This is part 2 of lesson 4 using loops. Please make sure that you have watched all the previous videos before watching this part 2 of lesson 4. In this video, we are going to learn for loops, demonstrate how to add a conditional terminal to a for loop, and describe how numeric conversion occurs on the for loop count terminal. So we will study conditional terminal in for loops and count terminal numeric conversions. Okay, conditional terminal. You can add a conditional terminal to configure a for loop to stop when a boolean condition or an error occurs. A for loop with a condition terminal executes until the condition occurs or until all iterations are complete, whichever happens first. So you see, when you right click the border, click the condition terminal, you get like this. Now you see this corrigent dot shows that condition terminal has been activated and this is the conditional terminal. So now either 100 iterations gets completed or the user presses the stop button. Whichever happens first, the loop will stop. Alright, so this for loop generates a random number every second until 100 seconds has passed or until the user clicks the stop button. Alright, so for activating the conditional terminal, right click the loop border and select the condition terminal from the shortcut menu. This is how you activate the condition terminal of a for loop. And this origin dot red glyph appears in the count terminal and a condition terminal in the lower right corner appears after the condition terminal for the for loop is activated. Alright. Count terminal numeric conversion. If you wire a double precision floating point numeric value to the count terminal, LabVIEW converts the numeric value to a 32-bit signed integer. You see this collision dot, this floating point double precision is converted into I32. So if you connect I32 with this number of iterations and terminal of the for loop, you do not get collision dot because it is its natural data type. So here you get a corrigent dot. For better performance, avoid corrigent dot by using matching data types or programmatically converting to matching data types. You see, this is a good practice to use matching data types, which is basically I32. And if you are using DBL, floating point double precision, then you need to convert it by using conversion palette and numeric and convert it into I32 to avoid the corrigent dot. Alright, now we are discussing timing a VI. Objective is to identify scenarios that require loop timing and apply the appropriate function. We will study reasons to use timing and wait function and express VIs. Okay, this is a very important question. Why do you need timing in a VI? When a loop finishes executing an iteration, it immediately begins executing the next iteration unless it reaches a stop condition. If you are acquiring data and you want to acquire the data once every 10 seconds, you need a way to time the loop iteration so they occur once every 10 seconds. You also want to time a loop to provide the processor with time to complete other tasks, such as processing the user interface. See here, in this example, this loop will chart a random number once every 100 milliseconds. So this is a timing functionality. It ensures that after every iteration, it takes almost 100 milliseconds and then next iteration begins. So This loop will chart a random number once every 100 milliseconds due to this timing Vi. Similarly, this is elapsed time express Vi. This loop will chart a random number until 10 seconds says elapsed. When 10 seconds completes, then it will get true and this loop will stop after 10 seconds. So this will chart a random number until 10 seconds elapse. When 10 seconds elapse, this loop will stop. So this is the functionality of timing in a VI. So you can say that we need timing in a VI basically for two purposes. First purpose is control the frequency at which the loop executes. Say suppose you want to insert a PID loop and you want that PID loop controller should work at the 5 kilohertz loop rate, so you will set the timing accordingly. Or you want to acquire signals from external hardware at a rate of 10 kilohertz, you will set the loop timing accordingly. So this is why you use the timing in a VI to control the frequency at which the loop executes. Or the second reason is give the processor time to complete other tasks. Alright, so let's move ahead. Wait function inside a loop. You can use wait until next millisecond multiple. So what is its behavior? Its behavior is basically it monitors a millisecond counter and waits until the millisecond counter reaches a multiple of the amount you specify. This function is synchronized to the system clock. Alright, and wait millisecond waits until the millisecond counter counts to an amount equal to the input you specify. And this time delay express Vi, this is similar to wait millisecond function with addition of built-in error clusters. These are the error clusters. So this is same as wait millisecond, but it has error clusters. And this is express Vi, time delay express Vi. Alright, so wait functions timing. Now basically, you see in this slide, the x-axis represents the value of the system millisecond timer. For this timing chart, both timers, wait until next millisecond multiple and wait millisecond, both are configured with input values of 100 and begin executing at time 50 milliseconds. They execute at time of 50 milliseconds. The wait until next millisecond timing function finishes its first execution in 50 milliseconds because 100 is the next multiple of 100 because you have specified 100 millisecond, so 100 is the first multiple of 100, therefore 100 is the next multiple of 100. For the second loop iteration it will finish at 200 and for third it will finish at 300. So because it is the next multiple of 100, this function is synchronized to system clock. Wait until next millisecond multiple is synchronized to system clock. But what happens in the case of wait millisecond, it also begins at 50 millisecond and it runs for also 100 millisecond each time, so it finishes at 150 millisecond because it's not multiple, it's simple wait millisecond. So if you start at 50 millisecond, it should stop first iteration after 150 millisecond. So because you have set it for 100 millisecond and the next will be 250 millisecond and next will be 350 millisecond. This is the difference between wait until next millisecond multiple and wait millisecond. Alright. Elapsed time express Vi. Basically, it determines how much time elapses after some point in your Vi and keeps track of time while the Vi continues to execute. See here, in this case, in this while loop, this loop will chart a random number until 10 seconds is elapsed. As the 10 seconds elapse, after the 10 seconds, this loop will stop because this time has elapsed will be true and this loop will stop. If you make it 20 milliseconds, so this loop will chart a random number until 20 seconds has elapsed. So you can vary the time target from here. So this is a function of elapsed time express VI. That it determines how much time elapses after some point in a VI. And as soon as that time elapses, if you connect it with the condition terminal, the loop will stop. All right. So demonstration, we will compare and contrast using a wait function and elapsed time express VI for software timing. Why software time? Because this VI is actually at this time running in PC. So now see the difference between wait until next millisecond multiple and elapsed time express VI. Now you see this loop will chart a random number once every 100 milliseconds and for 100 iterations. So if it chart a random number once every 100 milliseconds and for 100 milliseconds, so overall the time will be round about 10 seconds. And this second bottom while loop, what will happen in this while loop? This is for loop and this is while loop. What will happen in this while loop? This will continuously chart a random number without any delay until 10 seconds has elapsed. As the 10 second elapsed, this will stop. So let's run it. See the behavior, see the demonstration. This charts a random number after once every 100 millisecond, and this charts random number as quick as possible, but after 10 milliseconds it has to stop. Now you see after 10 seconds both stop, because if you chart a random number once every 100 millisecond for 100 iteration, it will be total 10 seconds, and here it is also 10 seconds. If I change it to 20 milliseconds, so this will chart a random number until 20 seconds has elapsed. See it. See the behavior now. Its behavior is same because I have not changed this, but it will now execute up to until 20 seconds has elapsed. So this is a function of this elapsed time express VI. See, 20 milliseconds completed and then it became true and the loop stopped. Alright, now we are discussing an important concept in LabVIEW, that is data feedback in loops, also called shift registers. This is a very important concept. We will learn apply shift registers when appropriate and predict the correct value at different iterations of the loop. You will cover introduction to shift registers, choosing shift registers, creating shift registers. Alright. So, introduction to shift registers. Shift registers store data values from previous iterations of a loop in LabVIEW. So, I repeat, shift registers store data values from previous iterations of a loop in a LabVIEW. So this is the purpose of the shift registers. Now see here, shift registers are similar to static variables in text-based programming languages. Now what happens in shift registers? Shift registers basically store values from one iteration to the next iteration. Write stores data on completion of an iteration. Write stores data on the completion of an iteration. Left provides store data. Left provides store data at the beginning of next iteration. So this stores data at beginning of the iteration. So this stores data at the beginning of the iteration, and this stores data on completion of the iteration. Alright, so this is the concept of shift register. Let us see a multimedia file for further clearing the concept of shift register.
After completing this module, using shift registers, You will be able to recall how shift registers store and pass data from one loop iteration to the next, and will be able to predict the correct value of a shift register at different iterations of a loop. You'll learn how to use uninitialized, initialized, multiple, and stacked shift registers. Sometimes when you program with loops, you need to access and use data acquired in a previous loop iteration. For example, if you need to get the average of several temperature readings, you would need to use the value from several previous loop iterations. LabVIEW uses shift registers to store and transfer any type of data, such as numeric, Boolean, or string. Shift registers appear as a pair of terminals directly across from each other on the vertical sides of the loop border. When a loop iteration completes, the shift register terminal on the right border transfers data to the shift register terminal on the left border to be used when the loop iterates again.
So this is the shift register. When the loop completes, this data stored in this shift register will be feedback to here, and when the loop will iterate again, that data will be supplied to the node. This is the concept of shift register. So shift register basically retain values of previous loop iterations. So it can store numeric, Boolean, and string data types.
Let's take a look at an example of using shift registers with a for loop. The for loop shown here is configured to run 2 times and add 3 to the value passed from the shift register each time. Because the left shift register is not initialized, it has a value of 0 before the VI runs the first time. During the first iteration, the VI adds 0 and 3. The value of 3 is passed to the shift register and used during the second iteration of the loop, this time adding 3 plus 3. After the VI completes, the value of the output indicator is 6. Because the shift register is not initialized, when you run the VI a second time, the right shift register holds onto the value of the last iteration, 6 in this case, and passes it back to the left shift register. So the second time the VI runs its 2 loop iterations, the value of the output indicator is 12. The default value of an uninitialized shift register for a numeric is 0. For a string, the default is empty, and for a Boolean, the default is false.
Okay, for a numeric, the default value is 0. For Boolean, it is false, and for a string, it is empty. So in this case, if you hit the run button for the first time, if it is uninitialized shift register, like here you see this is not initialized shift register, so the default value will be 0. 0 plus 3 will be 3, and during the second iteration 3 plus 3 will be 6, so here the 6 will be stored. If you now click the run button again, this 6 will be transferred here. 6 plus 3 will be 9, and 9 plus 3 will be 12. This is how uninitialized shift registers work in LabVIEW.
Take a look at this block diagram and determine what value is displayed in the output indicator when the VI completes.
So you see here it should operate for 5 times, is that, and number of n is 5. So 0 plus 1, 1, 1 plus 2, 3, 3 during first iteration, then second iteration 3 plus 1, 4, 4 plus 2, 6, 6 plus 1, 7, 7 plus 2, 9, 9 plus 1, 10, 10 plus 2, 12, 12 plus 1, 13, 13 plus 2, 5, 15. So after this loop executes 5 times, it should show output of 15. So 15 is the correct answer. 15 is the correct answer. You see? 1 plus 2, 3. Second time 3 plus 2. 3 plus 1, 4, 4 plus 2, 6. 6 plus 1, 7 plus 2, 9. 9 plus 1, 10 plus 2, 12. And last time it will be 12 plus 1, 13 plus 2, 15. Alright, continue.
What value is displayed after the same VI runs a second time?
If you hit the run button second time, now here you see the output was stored 15. So this 15 will be feedback to here. 15 plus 1 will be 16 plus 2, 17. 17 plus 1, 18 plus 2, 20. 20 plus 1, uh, 20 plus 1, 21 plus, 15 plus 1, 16. 16 plus 2, 18, 18 plus 1, 19, 19 plus 2, 21, 22 plus 24, 24 plus 1, 25 plus 2, 27, and 27 plus 1, 28 plus 2, 30. So if it again runs for 5 times, so this 15 will be stored back here because it is uninitialized shift register. So if you if you run it for second time, it will start from 15. So 30 is the right answer. You see, 15 was already stored. If you run second time, 15 plus 1 will be 16 plus 2, 18, and onwards it will execute. Alright.
If you want the loop to start with the same value each time the VI runs, you can initialize the shift register with a control or constant to reset the value for the first iteration of the loop. Here, the shift register is initialized to start with a value of 1 when the loop runs the first time. This means that when the VI completes, the value displayed in the output indicator is 5.
Alright, 1 plus 2, 3, second time 3 plus 2, 5. So you can also initialize shift registers. If the shift register is initialized, if you run it second time, it it will start with the value of 1 because 1 is the initialized value of the shift register. So shift register is initialized to start with the value of 1 when the loop runs for the first time. When the VI completes, the value displayed in the output indicator is 5.
Take a look at this block diagram and determine what value the output indicator will display after the VI runs one time.
If it runs for one time, then 3 plus 1, 4, 4 plus 1, 5, 5 plus 1, 6, 6 plus 1, 7. 7 should be here. You see, it's correct.
What is the value of the output indicator after you run the VI a second time?
If you run the second run button, if you click the run button second time, now it is the initialized shift register. It will again start from 3. 3 plus 1, 4, 4 plus 1, 5, 5 plus 1, 6, 6 plus 1, 7. So if you run it again, it will show again 7 because it is initialized shift register. So this is the difference between, please note the difference between the initialized shift register and uninitialized shift register. You see, this is the correct answer.
A loop can contain more than one shift register. If you have multiple operations that use previous values within a loop, you can use multiple shift registers to store the data values from those different operations. Notice that the shift register pairs are directly across from each other on the edges of the loop. The value of a shift register is stored and passed to its paired terminal directly opposite it on the loop. Here we are keeping the value of the add operation and the multiply operation. The first iteration of the loop stores a value of 2 in each shift register and then forwards those to be used in the next iteration.
Alright. So you can also use multiple shift registers. A loop can contain more than one shift registers. Shift register pairs are directly across from each other on the edges of the loop.
A loop can also contain what are called stacked shift registers, which retain values from multiple previous iterations. The most recent iteration value is stored in the top shift register, and as the loop continues to run, the value from the previous iteration is passed down the stack as new values are added. In this example, the shift registers are initialized as shown with the values of 2 and 1. The value stored in the right shift register after the first iteration of the loop is the sum of 2 and 1, or 3. On the next iteration of the loop, that value, 3, is passed to the top shift register on the left, and the value currently stored in the top shift register terminal, 2, is passed down the stack. The value in the second shift register is lost after this iteration, since we are storing only 2 previous values. On the third iteration of the loop, the value of 5 is stored in the top shift register, and the value of 3 moves to the bottom shift register. The result of the third iteration is a sum of 8.
Alright, so you can also use stack shift register to retain values from multiple previous iterations.
Take a look at this block diagram and determine what the values in the left shift registers and the output indicator are after 3 loop iterations.
So during first loop iteration it will be 1 plus 2 3, 3 plus 1 4, 4 will come back. So it will be 4 plus 1 here, 4 plus 1 5, 5 plus 1 6. Okay, 6 and bottom will be 4, 6 plus 4 will be 10, 10 plus 1 11. So output will be 11, top will be your 6 and bottom will be 4. So this is the correct answer. You see? So you can use stack shift registers to contain previous multiple iterations of the loop iterations. Alright.
You've completed this module. Here is a summary of what you've learned.
So you have learned how shift register store and pass data from one loop iteration to the next iteration. You have also used shift register can be initialized and can be initialized. Initialized shift register start with the same value every time the loop runs, and loops can also contain multiple shift registers to retain multiple values. Stack shift register retain values from multiple previous iterations, and how to predict the correct values of a shift register at different iterations of a loop. These things you covered in this module. Now let us let us see how we create shift registers in LabVIEW. Let me demonstrate. For this, I am creating a for loop. Let us initialize this and create constant here and make it for 5 times, and let us create a shift register here. Right click, create a shift register, go to numeric palette, take increment function, click with shift register and create indicator here to see the output. This is basically output. Okay. All right. So you see when I now hit the run button, it is uninitialized shift register, so it should start by default value of 0. So when it runs for 5 times, it should show me output of 5. You see, 5 is the output. Now when you hit the run button second time, this 5 will be feedback to here because it is uninitialized. So next time it will show me 10 here if it is uninitialized. See, 10. If I again hit the run button, this 10 will be feedback here. If it runs more for 5 times, the value will be 15. See, this is 15. And again, if I run it, it will increment by 5, 20. And this is for now uninitialized shift register. Now I can initialize it by creating constant. Let us initialize with 0. So if I run this button, it should output of 5. Now if I hit it second time, run button, it should again show me 5 value because it is an initialized shift register, and every time I hit the run button, it should initialize with the value of 0. See, I get 5 answer every time. Okay. Furthermore, you can create a stack shift register to retain previous from multiple previous iteration. So say suppose this is the top iteration. Create indicator here. You see this is top iteration, and this should show me 4 because here the topmost value will be 4. This is top iteration 4. I can even create a stack shift register to see data from previous iterations. Now this create indicator here. This is the previous iteration of previous iteration, and it should show me what value. If there is for 4, there should be 3, and it shows me error here. When you see error, the error is because if you are initializing, then you should initialize all these stack shift registers together. Now error is removed. Now hit the run button. You see here the value is 3. So you using the stack shift register, you can retain values from multiple previous iteration. This is the concept of stack shift register. All right. Okay. So we covered this multimedia using shift register slide, and we also demonstrated how to use this shift register in LabVIEW. We also discussed uninitialized shift register in LabVIEW and initialized shift register as well in LabVIEW. Now we are discussing exercise 4.2, calculating average temperature. Use a while loop and shift registers to average data. Okay, now we will perform exercise 4.2, calculating average temperature. Alright, let us refer to participant guide for this exercise. This is basically okay. The goal of this exercise is to use a while loop and shift registers to average data. Scenario is that the temperature monitor VI acquires and displays temperature. Modify the VI to average the last 5 temperature measurements and display the running average on the waveform chart. This is the waveform chart, temperature history. This is thermometer demo. This is temperature monitor VI that acquires and displays the temperature. And you have to perform the average on the last 5 temperature measurements. So figure 4, it shows the temperature monitor VI front panel and block diagram. This is the design. To modify this VI, you need to retain the temperature values from the previous 4 iterations of the while loop and average the values, as you have to find the average of last 5 temperatures. To accomplish this, you modify this VI as follows. Use a shift register with additional elements to retain data from previous 4 iterations. Initialize shift register with a reading from the simulated thermometer, this one. Calculate and chart only the average temperature. Okay, so let us complete this exercise in order to perform the average on these uh, last 5 temperature measurements and display the average on the waveform chart. All right. So for this, uh, go to the exercise core 1 and temperature monitor directory and open this LabVIEW project temperature monitor. I have already opened it, and then open the VI temperature monitor VI. This is the front panel and this is a block diagram. This simulated thermometer VI displays the random temperature. If you run this VI, you can notice the variation in the simulated temperature reading. Run it. You see this is the random simulated temperature shown here on the waveform chart named temperature history. So notice the variation in the simulated temperature readings. Stop the VI by clicking the stop button on the front panel. Okay, now modify this VI to reduce the number of temperature spikes, because if you take average, these spikes will reduce. All right, so display the block diagram, maximize it, modify the temperature. this block diagram Vi in order to perform average temperature. Okay, for this take this simulated thermometer demo sub Vi outside and then create the shift register. A state shift register should be created here to collect multiple temperature readings. Right click the border of the while loop, add the shift register. This is the shift register, and drag the lower resizing handle of the shift register to display 4 shift registers, and it becomes staked shift registers. Drag it to display 4 shift registers, and then connect them all. Initialize them. Alright. Now create a copy of thermometer demo Vi. Press Ctrl while dragging the sub Vi outside of the while loop and create a copy. The thermometer demo Vi returns one temperature measurement and initialize the left shift register before the loop starts. So drag it here inside the while loop, connect it with temperature history. Sorry, do not connect with temperature history, rather keep it here and then connect it with the here. So it initializes the left shift register before the loop it starts. Now take compound arithmetic from the numeric subpalette. There should be 5 elements, 3, 4, 5. 4 values from here. One minute. Let us wire it again. Alright. And then you should display the average divided by 5. Go to numeric, go to divide function, create a constant here, average of these 5 temperature readings. So this is average, and then click connect here. Alright. So divide returns the average of last 5 temperature readings, and that are displayed on this temperature history chart. Notice that you can create stack shift register terminals on the left side of the loop to remember multiple previous iterations and carry those values to the next iteration. This technique is useful for averaging data points. Stack shift registers can occur only on the left side of the loop because the right terminal transfers the data generated from only the current iteration to the next iteration. Okay, save this Vi. After saving this Vi, then run this Vi. Alright, run this Vi. Now you see average of these 5 iterations. During each iteration of the while loop, the thermometer demo Vi takes one temperature measurement The VI adds this value takes one temperature measurement. The VI adds this value to last four measurement values stored in the left terminals of the shift register. The VI divides the result by 5 to find the average of the 5 measurements. The current measurement plus the previous 4. The VI displays the average on the waveform chart, temperature T. This is waveform chart. Notice that the VI initializes the shift registers with a temperature measurement. So you see, this is the result you get on the scope. It takes iteration after every 1000 millisecond. Alright. Stop the VI by clicking the stop button. You can also create this waveform chart by going to data operation and clearing chart. You can make this loop to run little faster to take iteration after every 100 millisecond rather than 1000 millisecond. Now this loop should run faster than previous. You see, this is faster. Even you can make it faster by making this 100 millisecond to 10 millisecond. And you can again clear this chart by going to data operation and clearing the chart. Run it again. You see, this is even faster. Alright. So you are seeing the average of last 5 temperature readings from the VI, and averaging is performed with the help of concept of shift registers. Stop this VI, save and close the VI and project. Thank you very much. We will continue our lecture of lesson 4 in our coming last part of the video. Thank you very much.